It contains sequence of the independent steps. It is much easier to deal with the complicated systems using the state space. To design a control system, a real implementable control system for reality, we need to take 4 steps as a whole control system design. The first step is to determine the control or calculate the control law. To calculate the control law calculate the control law needs the information of the all states of your system. As I said before, the state of the system comes from the physics of the system. They are, for example, displacement or velocity for the mechanical applications. But in reality, most of the time it's not possible to measure the all state of the system. Why? The first reason is cost. Because if you want to measure the all state of the system, for example, if you have the 4th order system, you need at least 4 sensors. If you have the 8th order system, you need 8 sensors. So by increasing the number of states of the system, the number of the sensors will increase. So it means increasing the cost of the system. In reality, sensors most of the time are very expensive. Another reason is that sometimes there is no sensor to measure the states. For example, if you want to measure the absolute velocity of a system, we don't have any sensors, commercial sensors, to measure the absolute velocity. We can measure the relative velocity, but the absolute velocity is not possible. Or absolute displacement. We don't have any sensor to measure them. But relative, yes, we can measure them. If you want to measure the absolute velocity of a vehicle, for example, what's the best choice to measure the absolute velocity of an automotive, for example? If you, pardon? No, it's not the GPS. Well, what's the problem with GPS? It's not expensive anymore.
It takes a while to get the signal.
It has some delays, correct? But the most important one. What?
It's not very accurate.
It's very accurate. It's very accurate.
Is there some purpose?
Pardon?
Is there some purpose to the added mistake?
No. It's not right. There are high possibility you lose the signal. If you lose the signal, the whole control system will diverge. Okay? So that's why you need to have an alternative method to make sure that all states are measurable or the information from the all states are available. How we can do that? Before that one, let me give you a definition. The purpose of the control law, as the same as the Laplace domain, is that to transform or relocate the poles of uncontrolled system to locations that give us a desirable response. So in control law, doesn't matter in time domain, in the Laplace domain, the purpose of the control design is to rechange or relocate the location of the poles to regions that give us a desirable response. So we have the same control objective. The second purpose is, the second step is to design an observer or estimator. Observer or estimator estimate the response of the system using the minimum number of sensors that are available. The minimum number is 1. Higher number of the sensors, more accurate information. Lower number of the sensors, lower accuracy. Depends what is more desirable for you. If accuracy is not that much important, you can use minimum number of sensors. Using the sensors, you estimate the response or time response of the other states. I won't talk about the observer or estimator design in this lecture, but just to give you an idea how the whole control system works. The third step is to combine the controller and estimator together to build up the whole control system or whole control law. The last part is to design a controller in the case that we have the reference tracking system such that we have accurate reference tracking. Again, I won't talk about these 3 steps in this lecture. If you take the mechatronic module, I will teach these steps. But for this module, I will focus on the first part, just the control law design. It means in control law design, I assume that all states of the system are measurable or information are available. So, in the time domain, usually we call the full state control law plus observer, the whole control module, as a compensator. So if you heard the compensator is the control module including observer, combining observer and control law all together. How does it work? We have a system which has been modeled by in the state space form as the x dot equal to fx plus g. U is the control force, g is the input vector, f is the system matrix, and x is the state vector of the system. The output of this system is the state vector. In fact, we solve this differential equation. By solving this differential equation, I can find x. To solve this differential equation, you need to use the numerical methods. What's the simplest numerical method to solve this differential equation?
Euler method.
What?
Euler method.
Laplace transform.
No. Numerically, by computer, by MATLAB.
Matrix.
Which is the step method.
Is the finance difference. Do you know what's finance difference?
Mhm.
Okay, if you don't, look at the video I posted on YouTube, I think, beginning of the lecture. It's very easy. It says that, let me explain to you. Where's the eraser? It was some eraser. Okay. We can do something. Just a moment. Okay. Good. So, look, what's the definition of a differentiation of a variable? If I have xt, how can I calculate the x dot t?
Get the next time.
Xt, x dot t is xt at current time minus xt minus 1, the response 1 step before, over delta t, or over dt. In fact, the accurate is x dot t is limit of xt minus xt minus 1 over dt when dt goes to 0. Right? As an approximation, I consider this one. So xt minus xt minus 1 will be equal to x dot t delta t. Correct? So xt will be equal to x dot t delta t plus xt minus 1. So you need to use this formulation in MATLAB code. If you use the MATLAB code to calculate the xt based on the given initial condition, you need to put in the loop from t equal, for example, 0 to 10 seconds, and give the assumption, for example, x0 is 0 or whatever, and then start calculating xt. Yes?
Yeah, the numerical method, we would like this forward difference, backward difference,
Yeah,
central.
We call it the final difference.
Do you recommend using one of the three?
The- Look, this one is the easiest way to calculate the xt based on the differentiation. But the problem is delta t. If delta t is not enough small, you will have a huge error. Numerical error, not the analytical error, numerical error. Delta t should be small. For example, 1 millisecond is enough. But the point is that sometimes this differential system is robust against the variation of this delta t. if you assume very small delta t, you will still have the huge error. In such case, it's better to use the more advanced numerical methods, such as Range-Kutta. In MATLAB, we call it ODE45. Okay, if you use the command ODE45, you can solve the differential equation. If you have the linear system, this final difference is enough. But if you have the nonlinear system or complicated system, for sure you need to use the ODE45 to solve the numerically differential equations. Okay, so where's the lecture note?
Maybe
Yeah, it's uploading. Okay, so till it come up, is any question? No question? Okay. Okay, here you go. So, by solving this differential equation, I can find the state vector x at each time instant. If I calculate x, multiply x to h, what I will get, assuming there is no relation between the output and input, y. I will get the output of the system. Y is equal to hx plus ju. If j is 0, it will be y. Using the information I have from the output, y, which is one of the state of the system, I can build up a module, observer module, to estimate the whole state of the system using the output y. Look, x is the state vector. But I don't have, in reality, I don't have information from all elements of the items of x. So if y, for example, look, y is, as an example, is 1, 0, 0, x1, x2, x3, which means y is equal to x1. I can measure x1, but I don't have any information for x2 or x3. How can I get the information from x2 and x3? By building up an observer. The estimated x state of the system goes to the control module, which is in the form of minus kx hat. I will explain how to calculate the control law. And I can find the u as the input to the system if I have a regulator. This one is not for the reference tracking, it's just for the regulator. The regulator, it means that I want to force my state to the 0 or to equilibrium point as soon as possible. Okay? So this is the whole structure of control module, a real control module or implementable real module. In most of the industries, in most applications, aerospace, automotive, biomedical, this part is easy. And they have very sophisticated control system design, very advanced control system. The problem is here. They can't estimate or measure the state of the system. That's why most of the automotive doesn't have a very advanced control system. They have controls, but they are very basic. Yep.
Can you put a real life example to that system?
For that system, your project. Quarter project.
Yeah,
The real part. Yep.
It's a bit like just so that I can see it.
Okay. For your system, for the suspension system, for example, the one project we are doing with Jaguar Land Rover is exactly your coursework, but not that much simple. A very advanced control system, but it's using this structure. The state of the system, if you depends how you can define the state of the system. If you look at the references I gave to you, is most of the publication I made. You have the different chance of defining the state of the system. But the most appropriate and most practical is z.s as the S prime mass, displacement, and velocity, and suspension deflection. Delta Z, Zs minus Zu, Z dot S minus Z dot U. In reality, the only state that you can measure is the Zs minus Zu using LVDT. What's LVDT? Linear variable differential transducer. You have just sensor for this one, but the rest is not measurable. You can estimate Z dot S minus Z dot U using an advanced differentiator, as we discussed again in the module. What was the problem with the differentiator? It magnifies noises. Okay, so we can use this first order. To look, it is based on this relation. We can't calculate the X dot because it magnifies the errors. We need to use the 5th or 6th order differentiator. If you look at the paper, the references I give to you, you see the differentiator. To estimate Z dot S minus Z dot U. But for the ZS, Z dot S, because they are absolute displacement and absolute velocity, we don't have any sensor to measure them. How can we estimate them? Using the output. Usually the output is the displacement of the chassis, which can be measured or can be estimated by an IMU. You know what's the IMU?
Initial measurement.
Inertial measurement unit. Inertial measurement unit gives you the vertical acceleration. Based on the vertical acceleration, you can estimate the Zs and Z dot S. So it gives you the whole module. Or you can use the state of the system, Zs, Z dot S, Zu, Z dot U. In reality, if you use the Zs, Zu, Z dot S, Z dot U, none of them are measurable. Because you have the absolute. What you can do, you use the 2 accelerometers, one on the chassis corner, S-prime mass, and one accelerometer on tire, wheel hub. And based on the acceleration of these 2, estimate the other state of your system. Okay? Is that clear?
So when we write the state space function or whatever, do we need to take that into account? For example, in our coursework?
No. In your coursework, as I said, I won't talk about. Are you assuming that the whole states are measurable? In your coursework, you don't need to consider that one. I'm just telling you this strategy to have idea what's the real control system. How does it work? Okay, so as I said, so the whole module is called compensator. In reality, if you want to implement this controller, you don't have this part. This structure is good for the simulation purposes. But in reality, you have the actual suspension system or actual application. This is hardware. This part is software. You write the codes in MATLAB, compile it to the C++, implement it to DSpace or a microcomputer, and put it in the contract in the system. For example, CPU and not CPU. What was the name of the
ECU.
ECU, electronic control unit. Okay, you compile to electronic control unit. Sensors give you information to the ECU. Based on the information, you have the control logic, estimator or whatever, control logic. Control logic calculates the force. Force goes to the actuator, and the actuator generates the proper force to adjust the performance of your system. For example, actuator. For suspension system, you can have the hydraulic actuator, or you can have MR damper or ER damper, semi-active suspension system to control the system. Or you have the airplane, you have mini hydraulic actuator to control the system. So the controller, this is software again, ECU. Calculates the control action goes to the actuator produces a proper force to control the system. Here, in reality, this is the hardware. Okay, and here are the output from sensors. Again, hardware. But this part, the highlighted part, is software part. ECU or any other system that you have. Is that clear?
How does the price for compensator, for example, we have to buy microcontroller, right? How does the price compare with PID? Because the PID we can just build on top amps that are really
Look,
cheap.
as I said, PID is good for the simple applications. Okay? To be honest, for your coursework, you can use PID to design the suspension because you need to make many simplifications. as you're seeing in solving the system. For the practice is good, but in reality it's not good. Because for the suspension you have the multi-objective system. You want to reduce many things. Suspension deflection, suspension velocity, and suspension acceleration. Using PID you can't do this optimization. But using the state space, you can do. PID is good if you have the single input, single output system. But if you have the multi-input, multi-output, instead of just one output, you have different outputs. Instead of having one input, different inputs, or if you have the nonlinear system, you have to use just the state space format. You can use PID controller. Okay, any question? So, as I said, in this lecture, we consider full state variable feedback. We assume that the whole states are available, and we want to change the location of the poles of the system to the proper or desirable location to give to obtain a proper or desirable response. Again, assumption, we have access to the complete state XT for all time t. It means it's measurable. All states are measurable. The control law for the state space is minus kx. For the PID control, the control law was what? Proportional multiplied to error plus integral of error plus differentiation of the error. In the state space, u is minus kx for the regulator. K is the vector, which is the coefficient of each state of the system. If I have the values for the error states and calculate with k, I can calculate the control law. So, according to this relation, what's the objective? What's the main problem for finding the control law?
Determining
No. To calculate u, what should I have to do?
You have to find k.
You find the vector k. Exactly. Look, if I have a assume I have a PID controller. I have three gains, k1, k2, and k3. What's the state? Error, integral of error, and differentiation of the error. I can define three states and three gains. You can design a PID controller using the state space if your states are defined based on the error of the system or error of the signal. Okay, so determining the gain matrix K is the objective of the full state feedback design controller. Any question? Clear to everyone? Okay.
So,
Yeah.
that KX, is that related to FX or not?
What?
The KX that you showed us?
K? No. I will show you now.
The input.
I will show you now. Look, again, I have this system, uncontrolled system. If I assume all states are measurable, it means I don't need any observer or estimator. So what I can measure x. X is all state of my system. The control law is minus k, the vector that I need to find. Minus k multiplied to x give me the input u or control action u. Control action u. So if I have the system modeled by x dot equal to fx plus gu, again, we use this relation just for simulation. In reality, we don't have such a relation. We have a hardware, a physical hardware. But in order to simulate our control or system, we need to have some representation of the dynamic response of my system. The response is modeled by this state space format. The objective is minus kx. This one is software part of your real control system. So if I have the system x dot equal to fx plus gu. And if my control action gu is minus kx, if I put u equal to minus kx, I can factor out x. I will have a minus jk multiplied to x. Right? So control system, the matrix, the system matrix for the control system is a minus jk. For uncontrolled system, I have just a. Correct?
Where did you
So-
get the A from?
A is the system model, system matrix. X is equal to AX. Okay? But if I have the control, I can change the system matrix by JK. If I find proper gain of K, I can change the location of the system matrix. For the controlled one, sorry, I made a mistake. Here is F.
Ah,
Here is F. It's F minus JK. I made a notation. Some references use the notation A, B, C, D. Some of them use the notation F, G, H, J. Here, A is F. It's the if F minus JK. So, in order to find the pulse of the control system, I need to calculate the eigenvalues of F minus JK, the control system. I will explain this one in using an example to make clear to you. Okay, if I have such a system, the control system, the response of the control system will be e power f minus jkt xt naught. Everybody knows how we get the xt. Everybody know? Where does this relation come? I started here. Here. Where's all the system? The response will be ki e power pit. Ki is initial condition. E power pit. This one is the eigenvalues of the system, the poles of the system. Correct? So, given per fg, I think your lecture note you have A and B. It should be F and G. Okay. We can always determine K to place all the system close to poles in the left half plane if and only if the system is completely controllable. What does it mean the system is completely controllable? I avoid the mathematical definition of the controllability in this module. But keep in your mind, you can't control any kind of a system. The system should be controllable. It means that I need my control action somehow should have the ability of the controlling all state of my system. If there is no direct connection between the state and the control action, the system is not controllable. But as I said, this one is just to give you an idea. I won't talk about the concept of the controllability in this module. There is some mathematics. Maybe next week, just give you, but I won't ask you in exam about the controllability or something. Okay, so now let's see how the control system, how can I design a controller? What time is it? It's correct?
Yeah.
Okay. So we have to understand. Assume I have a dynamic system, a mechanical system. Its dynamic is given by this third order differential equation. Guys, this is the last part of your control module. Think about it and be happy with that. It's the last part. Yeah.
Will there be one last 40% question? Okay.
Maybe I asked, I need to see something. 40%. How can I design? You need to answer.
State space. State space. Huh? You go state space first.
Okay, what?
You need to go state space. Huh?
No, how can I find the how can I find the matrix gain K to design the controller?
Okay, you need to plot the poles, plot the zeros, and you know what I was explaining before.
I know, you're right, but no, to calculate K. Are you looking for just anybody? Anybody? 80%.
Oh, okay.
80%.
No, this is not.
How to find K?
Don't you like tune K once you
Yeah, how can I tune K?
through like interpretation?
No, I want to calculate
I'm
K.
not sure.
Find what the zero is.
Oh, here it is.
What?
See?
Okay, guys, 100%.
Don't do this.
Tell me.
You can't don't let him. I know.
Find the characteristic equation from the poles in this one.
Pardon?
And then find the characteristic equation. And then
100%. Well done.
No.
Well done.
No.
To find the characteristic equation. But like 100% was too much for that. Characteristic equation of what?
of the poles is the determinant of the SI
Okay, for what? For which systems?
steady state.
No, no. Characteristic equation of what system?
It's
It's correct. Okay, go ahead please.
the U of S, so GOS equals Y of S over U of S, and then the characteristic equation is U of S.
No, no, not using that. No, no, it's the right. Your answer is correct, but in SSS space format, not in the Laplace domain. What will be the characteristic equation in the SSS domain?
Oh, yeah, I know this.
No, 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 but I want to
The inverse of
The inverse of
I
that.
don't think I accept your answer.
SI minus F, the inverse of that.
Okay, for the uncontrolled system, for the control system, what's the characteristic equation? If you answer this one, you get the 100%. Otherwise, you get 50%. What?
U equals KX, and then it's
Okay.
K times SI minus F.
Correct, exactly. So you're done. Yeah, he deserves. Yeah, exactly. He deserves that one. Yeah, exactly.
100%.
But the point is that Daniel, you already have done most of the coursework.
It's a shame.
But you can help Alex to finish his
Yeah.
coursework. But well done.
I'm gonna
Great. Look, we have the characteristic equation, as I said. The characteristic equation for the uncontrolled system is determinant of SI minus F, and for the control system, it is determinant of SI minus F. What was that one? F minus JK. Okay? We need to compare these two characteristic equations, and using this characteristic equation, I need to calculate K such that I get the correct response. So I will explain here. I was surprised, Daniel. Well done.
It's just because of listening this lecture.
Okay. So I want to have the damping ratio of 0.8 and the settling time of 1 second. First, I need to calculate, to define the state of my system. X1 equal to Y. But you own Mark because he asked me to give 40%. But that's good. You won't get anything, Mark. Okay, x1, I define my set at x1 equal to y, x2 equal to dy over dt, and x3 equal to d2y over dt squared. If I define my state, I can form this third order differential equation as the first order differential equation here. Here, my system matrix is a 3 by 3 matrix, and I have a 3 by 1 vector as an input vector u. The output is y. So h is 1, 0, 0 multiplied to x. X is x1, x2, x3. I define k as a k1, k2, k3. I have a vector of 1 by 3 because I have 3 states. And the control law is u minus kx. So the objective is to find K using the characteristic equation, the poles locations. X dot is Fx minus JKX. U is minus Kx. So I put U here. F minus JKX. So this is the new system, the controlled system. To find the proper K, I need to deal with the poles of this system. I build up the F minus JK, which will be in this format. If you multiply J to K and subtract from F, you will come up with this matrix. To find the characteristic equation, I need to find the eigenvalues of the controlled system. This is the characteristic equation of the controlled system. For the control system, I want to have the damping ratio of 0.8 and settling time of 1 second. Again, the relations we obtained is for the second order system. Here we have the third order system. If I reshaped this third order system as a multiplication of the two complex conjugate poles and the one real pole. I assume my real pole has the same real part as the complex conjugate. This is just assumption. This is the design. It's not just calculation. You can't find anything, but in order to make this calculation simple, I choose the same third pole. You need to calculate the poles of this system, plot it in MATLAB. If your response is acceptable, it's fine. Your assumption is fine. If it's not acceptable, you need to change your assumption. Okay, if I assume the third order system, based on the relation, I have the Ts over 4 over zeta omega n, which should be equal, if I assume damping ratio is 0.8, will give me omega n equal to 6. I have damping ratio equal to 0.8 and omega n equal to 6. If I substitute here, I will come with this third order. Look, here is 2 zeta omega n will be 9.6, omega n squared will be 36, and zeta omega n will be 4.8. If I multiply this polynomials, I will come up with this characteristic equation. So this characteristic equation will give me damping ratio 0.8 and omega n equal to 6. Right? Yeah. Which one? I made almost 1 because if you put it equal to 1, you made some assumption. It's not correct. It's better to have higher values in order to make sure that we are in the region. And I said it's almost 1. It's not exactly 1. So this one will be my desired characteristic equation. If you compare this desired characteristic equation with this one, you need to have the same coefficients. So it means 5 plus K3 should be equal to 14.4. 3 plus K2 should be equal to 82.1. And 2 plus K1 should be equal to 172.8. If you do this calculation, you will get K3 equal to 9.4, K2 equal to 79.1, and K1 equal to 170.8. Here, the blue one, response of the uncontrolled system. The red one is the response of controlled system. No oscillation, very fast response. Look, compare this one. Settling time, look, the settling time for here is almost 12 seconds. The settling time is almost 1 second, as we expected. Okay? And damping ratio is higher than 0.8 because we don't have any oscillation. So the best response we want to get.
What is the blue one?
Uncontrolled system. There is no control system. but here is the control system. Look, you need to follow almost the same approach for the PID control server for the coursework. I will solve more design examples next week. Okay, to see how to design a real control system for the real application. Okay, guys, I hope all of you enjoyed control module.
Yes.
Good. This is the last thing. Right. This Thursday and next Thursday is your chance to work with the MATLAB code for the coursework. Okay, then we come to the job. And next week is the last week you will see me. I will be on the business trip. Week after, you don't have any chance to see me. So please come to the tutorial, and I will solve the problems on next Monday, 3 hours. Yes. No.
But
Next week is the last.
I'll say,
Just a moment.